Hello, my name is Danny Hewson, and I would like to talk about a galaxy of periodic tilings. Here's an outline of my presentation. We'll be moving from topology through geometry and combinatorics to algorithms and software. So let's start with topology. I'd like to talk about the classification of orientable closed surfaces. So the most simple such surface is a sphere. And in John Conway's notation, this is called 1. Here's a second orientable closed surface, the torus. Conway calls this ring, or uses the notation ring for a torus. A torus with 2 handles, in Conway's notation, that's ring, ring. And if you have H handles, then that is designated by H rings. Non-orientable closed surfaces, well, how do we get those? Well, we start with a sphere. Let's remove a disk from the sphere. So this is not a hole that goes all the way through and out the other side. It's just a disk, removed from the sphere. And now let's take a Möbius strip. We all know, and we all like Möbius strips. They have those nice properties that they're only one-sided. So if you start drawing on one side and go around, suddenly you'll be on the other side of Möbius strip. And also they only have one boundary component, which is a loop. So what you can do is glue this Möbius strip into that hole that we cut in the sphere along the boundary, and what you get is a sphere with what's called a cross cap. So a sphere with a cross cap, this is a projective plane, and here in this picture of the projective plane, you can see what a cross cap looks like, but I'm not good at drawing those kind of configurations, so I'm just going to use a circle with a cross in it for a cross cap. And in Conway's notation, this is cross. So with 2 cross caps, turns out that's a Klein bottle, and that's cross cross in Conway's notation. And then, in general, you have K cross caps, you then designate that by K crosses. We come to a theorem that people have long known about. Any connected closed surface is either a sphere with Conway notation 1, or a sphere with H handles, annotated, or notation is H rings, or K cross caps, K crosses. Note that there is no combination of handles and cross caps simultaneously, and we do not need to combine these, because if you have a non-orientable surface, then you can replace any handle by 2 cross caps. So if you have something like this, then that's the same as having a sphere with 7 cross caps. And if you think about it, it's quite easy to see if you look at the Klein bottle and what that looks like, compare that to a handle, and you will see that by cutting open a handle and then gluing it back together, but in the opposite orientation of the 2 circles along the 2 circles, boundary circles, you get a cross cap. No, you get a Klein bottle. So that's why you can trade any circle for 2 cross caps if there's a cross cap present. Now, what about surfaces with boundary? Well, here's an example of a sphere with 3 disks removed, and in Conway's notation, that would be 3 stars. There's a star for each boundary component. Here's a 2-handled sphere with 4 disks removed, so this would be ring, ring, 4 stars. And here's a non-orientable surface. And this would be with a hole with a boundary component, so this would be star cross. So, and this is, if you think about it, the Möbius strip again. So the theorem that we can now formulate is any connected surface, closed or with boundary, has Conway symbol 1 if it's a sphere, or it has symbol star, 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 B stars if it's a sphere with B disks removed, or it's H rings followed by B stars, where B is greater or equal to 0, a sphere with H handles and B disks removed, or you have 0 or more stars followed by 1 or more crosses. And so by convention, in Conway's notation, you first list any rings and then the stars, if any are present, and stars come before crosses. Now we're going to move on to the concept of orbifolds. So this is something that Bill Thurston was very interested in, so-called orbit manifolds. And we're going to look at this in a quite a naive way. So we're going to start with one of those surfaces. And here's the Conway notation for a torus with two boundary components, so ring, star, star. And to get an orbifold, we're just going to add a finite set of points with labels, and these labels are integers at greater or equal to 2. So look something like this, and there's a notation that corresponds to that, and that's what we're going to look at in detail now. So here is a torus with two boundary components, and we've added 3 points in the interior of the surface, and these are called gyration points, and you can see them here. So we're in this example, there are 3 gyration points labeled 2, 2, and 7, and points that appear on the boundary components are called corner points, and here we have 4 of those. And then there's a notation for describing these two-dimensional orbifolds. So after any rings, 0 or more rings, you list all the gyration values in any order you like. And then for each boundary component, you list the corner points on them in the order that you encounter them. And then depending on whether the surface is orientable or not, you have to make sure that you use consistent orientations on the different boundary components. So there's more to an orbifold than what I've described here, but this is all we need for this particular presentation. So think of it as a two-dimensional surface where we've added a finite number of points, some of them gyration points, other ones corner points. So here's Conway's orbifold notation. So in general, unless you have just a sphere which is has notation 1, your notation is going to look like this. You're going to have 0 or more handles, 0 or more gyration values, 0 or more boundary components. Some of those boundary components might have corner points associated with them, and then you have 0 or more cross caps, or it's just a 1 if you have none of those. Okay, so it was a little bit of topology. Let's move on to geometry. So those orbifolds are closely related to two-dimensional symmetry groups with compact fundamental domain. So what's a symmetry group? Well, think of a physical object like a table, and then look at all the symmetries of that table acting on an enclosing sphere. So in this particular case, if this were a rectangular table, then if you identify points on the sphere that are symmetry equivalent, then you get 1/4 of the sphere, and points in the interior of that 1/4 have 4 pre-image points. Points on the boundary have 2, and points on the top or the bottom have 1 pre-image in that construction. The top point and the bottom point correspond to twofold rotations, and the boundary points correspond to reflectional symmetries of the table. And so this gives rise to a disk with 2 corner points on the boundary. And so the symmetry group for this table is star 2, 2. And here I've just drawn it in that other way that we've been drawing things. Here's another example of how to get an orbifold from a symmetry group in this tiling here. Imagine it covering the whole of the Euclidean plane. There are some reflectional symmetries that I've drawn as lines here, indicated lines, and there are some twofold rotational symmetries for which those reflections pass. And then that orange region in the middle is a fundamental domain for this corresponding symmetry group. And so that is, the fundamental domain is basically a disk with 4 different corner points on the boundary. So this is symmetry group star 2, 2, 2, 2. Here's another example. We have some reflections and some threefold rotational centers. There's a fundamental domain here we have to identify along the dotted line. So what we get is a threefold. So the threefold rotation number 2 is not associated with any reflections. So it's gives rise to a gyration point, whereas the threefold reflection at positions 3, labeled 3, 1, also has reflections going through it, so it ends up on a boundary component. This is the symmetry group 3 star 3. Here we have another situation where some of the twofold There are some rotations that lie in reflectional symmetries, other ones that don't. So this turns out to be the group 2*22. Here we have no rotations. Here we have a reflectional symmetries in the one direction. That gives rise to a boundary component. And then we have a glide reflections in the other direction, which gives rise to the cross cap. Here we have glide reflections in two different directions. So we have two cross caps on this sphere, turns out, and this symmetry group has the name cross-cross. We can do that kind of determination of the symmetry group also from a hyperbolic tiling or hyperbolic drawing of a tiling. And in this particular case, turns out that we have one boundary component. To get this sphere with a hole in the right-hand side, we identify along the dotted line there in the appropriate way. There's a fourfold rotation here. There are no reflections that go through this center of fourfold symmetry, so that point ends up in the interior of the sphere. And there's a threefold symmetry here. And it looks like there's one here as well, but if you look more closely at the drawing, you see that this is the same point. And so there's only 1, 3 on the boundary component. And so the symmetry group here is 4*3. Okay, so we've seen that if we have symmetry groups acting on physical objects or on tilings and so on, that we can figure out what the orbifold notation is for the symmetry group. Now the question is, if I just have an arbitrary orbifold symbol that I've made up, does it always correspond to some group acting on the geometry? So the theorem says that any orbifold system can be obtained either from the sphere through identifying points using an orthogonal group, or from the Euclidean plane, modulo a crystallographic group, or from the hyperbolic plane, identifying using a non-Euclidean group. So any orbifold that you can make up, there's a symmetry group acting on a geometry that realizes that symmetry group, except for then there's a number of so-called bad orbifolds that do not arise, cannot be obtained in this way. For example, P, the teardrop orbifold. If you think of one way to see why that would be the case is that P, the teardrop orbifold would have to come from a group acting, an orthogonal group on the sphere where there's exactly one rotational point on the sphere. And if you think about it, for any point where there's rotational symmetry of the sphere, there's going to be an antipodal rotational point as well. Okay, we're still in the chapter of geometry, so we're going to, next part of the talk is going to be about these geometric objects, so-called periodic tilings, tilings with a compact fundamental domain. And so some of them will be spherical, Euclidean, or hyperbolic. And here I've listed their orbifold names for these particular tilings here. So let's move on to combinatorics. We're going to talk about periodic tilings of the plane. We're going to talk about so-called equivariant tilings. So what does that word equivariant mean? Well, it means that we're going to take a set of tiles, and they're going to be simple tilings with no unusual properties. I'm not going to go through the list of exactly what we're requiring here, but nothing strange is going to happen here. And we're going to equivariant because we're looking at the tiling together with a prescribed symmetry group. So the symmetry group could be all the symmetries that you see of the tiling, the maximal symmetry group, or it could be some subgroup of the maximal symmetry group. And so sometimes if we draw a tiling, it might look the same. Two different equivariant tilings might look the same because we're only drawing the topology and we don't see that some of the symmetries are missing in the one group that are present in the others, or vice versa. Okay, what we're going to look at now is how to capture the combinatorial structure, or the essence of a equivariant tiling. So here's an example. We're going to look at this example, and one way to approach this, or one way to describe this, is in terms of a barycentric subdivision. So we triangulate the tiling in this way by choosing a barycenter of each of the tiles and connecting to all vertices and edge centers. It's sometimes also called a chamber system in the context of the theory of buildings. Or another way to think of this is a set of flags, where a flag is a triple, in this case, a vertex contained in an edge contained in a face. So each flag has a 0, a 1, and a 2-dimensional component. And there's exactly one other flag that differs in exactly one of those 3 components. Now let's consider the orbit of these triangles in the bicentric subdivision, or the flags under the symmetry group. So I've just labeled things here 1, 2, 3, and 4 if they are symmetry equivalent. And here I'm using the full symmetry group, the maximal symmetry group of this tiling. So that's why I get 4 classes. And we're going to represent these orbits as nodes in a graph. So there's 4 orbits, and so I've drawn 4 nodes. And note that if you take one representative of each of these equivalence classes, then you get a fundamental domain for the symmetry group. Okay, so we're going to have a graph with 4 nodes. Each node represents a class of flags. And as I said, each flag has exactly 1, 0, 1, 1, and 1 2-dimensional neighbor. And so we're going to use edges labeled 0, 1, and 2 to indicate how triangles are neighbors to each other. So if you're in a triangle of type 1, you go to your 0-dimensional neighbor, exchange the vertex, then you come to another triangle of class 1. Same if you exchange the one-dimensional element, but if you exchange the 2-dimensional element, go to the neighboring triangle that's in a different face, then you leave class 1 and enter class 2, and then similar for class 2 and 3 and 4. So each node in this graph is incident to exactly one edge of labeled 0, one labeled 1, and one labeled 2, showing how the triangles represented by these equivalence classes neighbor each other in the tiling. So this is most of what we need. We need one more set of invariants. We need to record for each equivalence class of triangles the face degrees and the vertex degrees of the tiling that contains those triangles. So class 1 is contained in a hexagon. That's why there's a 6 here, and the adjacent vertice has degree 4. Triangles of class 2 and 3 are both contained in a tile with 4 edges and also adjacent to a vertex of degree 4 and triangle and degree 4. Okay, so this is called the Delaney-Dress symbol of the tiling. This is something that Delaney-Dress introduced in 1985. He named it after Matthew Delaney, who had looked into some ideas that inspired Delaney-Dress to come up with this concept. And so the Delaney-Dress symbol has a set of nodes, and it has a set of 3 types of edges. Andreas likes to describe this as a group action of 3 involutions acting on these elements. But quite often people like to describe this in terms of a graph as well. And then there's those 2 functions, M01 and M12, that record face degrees and node degrees. And there's a number of conditions that have to be fulfilled so this all fits together. And the key observation that Andreas made was that 2 equivariant tilings are equivalent of the same topology, and the group symmetry, the same symmetry group attached to the tiling in the same way, if and only if the Delaney-Dress symbols are isomorphic. So Delaney-Dress symbol captures the essence of such a equivariant tiling. There are some simple properties that you can immediately read off the Delaney-Dress symbol of a tiling. For example, if you look at the 0, 1 components of the tiling, you can see there's 3 of those here. 0, 1 means I'm moving from one triangle to the other without ever crossing into a different face. So obviously the number of such 0, 1 components is going to tell you how many faces the tiling has. And 0, 2 tells you about how many edges there are, and 1, 2 tells you about the number of vertices. There's slightly more advanced properties. Euler characteristic tells you something about the corresponding orbifold. The curvature is a value that is closely linked to the geometry. If you have negative curvature, then you will be a tiling that is realized in the hyperbolic plane. Zero curvature corresponds to Euclidean geometry, and positive curvature corresponds to spherical geometry. And you can also read off the orbifold name of the corresponding group from the Delaney-Dress symbol. So let's look at the curvature as an example. This is how it's computed. The sum of all elements of the Delaney-Dress symbol, adding these numbers up, the vertex, the face degree and the vertex degree. And as I said, this tells you what geometry the tiling will be realized in. Here's a difficult property that we've been looking at for a while, and I think you have a handle on it mostly, but it's quite a tricky one. A tiling is pseudo-convex if the intersection of any two tiles is either empty or connected. So this is pseudo-convex here. If you look at any two tiles, either they share only a vertex, or they share an edge, or they are disjoint. In this tiling over here, these two tiles, A and B, their intersection consists of this point here and this point here, so there's 2 points, so this is not a connected intersection. Figuring out whether a tiling has this property or not from its Delaney-Dress symbol is not immediately obvious how you do that. Simplest property of Delaney-Dress symbol is something that we'd like to call the dress complexity of the tiling. It's just how many nodes does the symbol have. So the simplest case obviously is you have one node, and then those three edges have to be self edges. And then there's a choice here only for those two parameters, P and Q, the face degree and the vertex degree. And so let's consider all cases. Let's discuss this briefly with P. Let's assume our tiles have at least 2 edges and vertex degree is at least 3. Then this is the curvature formula in that case, a very simple formula that you can then discuss in a case-by-case fashion. So if P equals to 2, then what this boils down to is 1 divided by Q, and that's always going to be a positive number. So if you've got digons, then the tiling has to be a spherical tiling. And this is what the tiling is going to look like. You've got a Q-fold rotational symmetry, and then you've got a 2-fold symmetry around the edge, center of an edge, and then the center of a tile, and then the tiles themselves are digons. And the symmetry group for that is star Q22. That's not true, huh? It's 2 star Q2. Okay, that's a, no, sorry, it is star Q22. Yep, it is correct. Okay, if P equals to 3 and Q equals to 3, plug in all these numbers, you get 1, 6. It's greater than 0, so the tiling is going to be spherical. And if you increase the vertex degree to 3, 4, or 5, it still stays positive. And so you have these 3 tilings here with these symmetry groups. If you increase Q to 6, we're talking about triangles, 6 at any vertex. And then you're looking at a Euclidean tiling. The curvature is 0. Go beyond 6, the curvature becomes negative. Say for 7, it's minus 1 divided by 42. So you have a hyperbolic tiling. And the bigger you choose, for any Q greater or equal to 7, that you have negative curvature and a hyperbolic tiling. Something interesting here we have an infinite family of tilings. And so we want to get a handle on those infinite families. And so we can introduce this concept. I don't know whether it's a good name, but we're going to call it geometry minimal. So Delaney-Dress symbol and all the corresponding tiling is geometry minimal if it's a spherical tiling where the rotational degrees, I haven't defined what these V01 and V12 are, but they are the rotational degrees in the symmetry group. So they have to less or equal to 5, so we don't never go beyond 5 for spherical tiling. Or we're talking about the Euclidean case, in which case all tilings are geometry minimal, or Delaney-Dress symbols are geometry minimal. Or in the hyperbolic case, and we can't reduce a rotational degree without changing the sign of the curvature or violating one of the properties of a Delaney-Dress symbol. Okay, so this is geometry minimal, because if we replace a 7 by a 6, then we switch to a Euclidean tiling, or the 3 by a 2, then we have a spherical tiling. We can't change the 2 because if we replace a 2 by 1, then we don't have a valid Delaney-Dress symbol. This guy over here, with this 10-fold rotation, we can replace 10 by 9. It's still hyperbolic, so this is not geometry minimal. Okay, so now with those definitions, we can come to the classification of geometry minimal tilings with Delaney-Dress, with dress complexity 1, and now we're looking at everything with P at least 3, so we're not looking at the Diagon case. And there's exactly 12 such tilings. As I said, some of these represent infinite families, but that's why we introduced geometry minimal. So there's 12 of those. Okay, complexity 2, turns out there's 50 such tilings. Complexity 3, there's 36 such tilings. You can see that, sometimes, the colors indicate that there's more than one equivalence class of tiles here. Things can look identical. You can't see a difference between this tiling here and that tiling here. And the reason for that is that we're only seeing the topology. We're not seeing exactly what symmetry group is meant here. You can see this has symmetry group star 632, and this has symmetry group 2 star 22, and we don't see how the symmetry group is attached to the tiling in these pictures. So you would have to go in there and deform some of the edges or add some icons or something in those pictures to make it clear which symmetry group is meant. That's the whole issue about equivariant tilings. It's a set of tiles together with a prescribed symmetry group. It might be the maximum symmetry group, all the symmetries that those tiles actually have, or it might be a subgroup with compact fundamental domain. Okay, here's dress complexity 4, dress complexity 5, dress complexity 6. You can see that numbers are going up quite rapidly. It always goes down a bit when you get to the odd numbers, because if you have an odd number of elements in the Delaney-Dress symbol, then you can't. Then the symmetry group is going to have reflections, and or it's going to have reflections. So it's just, that's why there's less of those. Don't have any orientable symmetry groups. Here's 8. Okay, we're already at 1200, and so you can see how this goes on. And so we did say let's enumerate all Delaney-Dress symbols up to the size of 24, complexity of 24. And we call this a galaxy of periodic tilings because for 2 reasons. First, the number is quite large. Obviously, 2.4 billion is not as big as the number of stars in a galaxy, but it's still a very big number. And secondly, because I've spent many hours looking at these tilings, and I guess it's a bit like looking at stars. They're all kind of slightly different, but they're basically the same. So there's a lot of, much of a muchness type feeling about these tilings. Yeah. So this number here, 2.395 and so on, billion tilings. This is not some number that we computed. This is actually all the Delaney-Dress symbols that we have a file on a server. So these are actual entities that we can look at. A couple of 100 gigs of data on a server. Of these 2.4 billion tilings, just over 2 million are spherical and 1.7 million are Euclidean. Okay, so that's something about how to work with symmetry groups and equivariant tilings and how to systematically enumerate tilings. And let's look at the details of some algorithms and software. So the program that enumerates the Delaney-Dress symbols was written by Olaf Delgado. He wrote it in Julia. And it uses the concepts from orderly generation. This is methodology that was developed in the context, I guess, of in general group theory, enumerating groups or computing the determining whether 2 groups are isomorphic or not. Yeah, so his code takes a couple of hours to compute those 2.4 billion tilings. I also wrote a program using a different approach in Java to solve the same problem. I got up to n equals or complexity 18, and that was kind of as far as I got with my code. But we did compare the output for complexity up to 18, and both programs produce exactly the same output. So that's some confirmation that these numbers, there's not an obvious programming error here. We developed, together with Rüdiger Zeller here in Tübingen, we developed a program called Tegula and a program called Tegula Design that you can use to visualize and explore those tilings. So Tegula uses as input a database of Delaney-Dress symbols. And it uses an algorithm for constructing a fundamental domain for a Delaney-Dress symbol. This goes back to Klaus Westphal's diploma thesis in 1991 that he wrote with Andreas Dress. And for all these years, I've kept a copy of his MS-DOS code, and I ported that from C to Java, and that's what we use in Tegula. And Rüdiger Zeller came up with code for copying fundamental domain to obtain the tiling, and there's a lot of geometry going on in the code. So this is what the program looks like when you fire it up. We ship it with a database of all tilings up to complexity 18, which is about 7 million tilings. You can open up a dialog where you can specify what kind of tilings you're interested in. So you click on different values here. I've said I'm interested with tilings. Well, there's 4 equivalence classes of tiles, 4 equivalence classes of edges, 4 equivalence classes of vertices, and I don't want them to be Euclidean, and I don't want them to be hyperbolic. So click that together, and what you see up here is a query to our database of Delaney symbols. So the program contacts that, opens that database file. In this case, it finds 295, so that is a mathematical result right there. There exists 295 tilings that have these properties and complexity greater, less or equal to 18. You can look at these tilings, say on page 4 here, I found this tiling, I like this tiling, I want to interact with it, so I can open up in a new tab, and I can, for example, modify its symmetry group. So you see over here, the symmetry group is star 532. If I replace one of these numbers, the 2, which is this twofold rotational symmetry here, by a 3, then I get a hyperbolic tiling. Very much the same tiling, except for where we had a twofold rotation, we have now a threefold rotation. I can change the hyperbolic model to say the Klein model, and there's a lot of other stuff I can do with this program. So I've recorded a short session here. So here I am saying I want 4 classes of tiles, 4 classes of edges, 4 classes of vertices. Each time I press return, the database is queried. I don't want Euclidean, and I don't want hyperbolic. Okay, so there's 17 pages of such tilings. I can page through them and then say, I like this tiling here. So double click on that. There you go, here's that tiling. And I can interact with the symmetry group. So here it's star 432. I replace the 4 by a 5, still spherical. If I replace the 5 by a 6, I have star 632, which is with a Euclidean symmetry group. I can, within the rotations, go into the fundamental domain and change the shape of some of the edges without changing the symmetries of the symmetry group. There you go. I change this 2 by a 3. I've got star 633, which is a hyperbolic group. So here's a part of that tiling shown in the Poincaré model. And the Poincaré model, in theory, you have to show all tiles, but I'm only going to show some of them, but you can control how much of the tiling is represented by pressing these buttons here. You move to the Klein model or the hyperboloid model. And we actually do all our computations in this model, and then we get the other 2 models simply by placing a projective camera at the appropriate location. There are some algorithms based on Delaney-Dress symbol. For example, you can orientate the symmetry group, which means you take out the reflections, you double the size of the Delaney-Dress symbol. Now, if we look at so the tiling looks the same, except that if we start interacting with a fundamental domain, changing the shape of edges and so on, then you will see that there are no reflectional symmetries anymore. Dualize, here's a dual tiling. You can pull those edges straight if you like, get something like this. And then there's ways to change the appearance. You can change to a different color scheme and change all kinds of properties. For example, you want to draw the edges thicker and give them a different color, say gray. And then there you go. There's a hyperbolic tiling that none of us has ever seen before. Tegula design, I'm trying to turn that into a program that might be useful for designers to produce more interesting images. Okay, we come to the end of the presentation. I first told you about Conway's orbifold notation, this two-dimensional symmetry groups. We saw that Delaney-Dress symbols can be used to describe equivariant tilings. I presented our galaxy of periodic tilings, all periodic tilings up to complexity 24. There's 2.4 billion of those. They're all in a big file on the server if you ever want to study them. I gave you a small demo of particular software that we've developed to visualize these tilings. And I'd like to thank you for your attention. Thank Rudy Gasella, who worked on this with me as a postdoc here in Tübingen, to students Julius and Cornelius, who contributed to the Tegula program, to Olaf Delgado for his classification software, to Klaus Westphal for his 1991 MS-DOS code, and to Andreas Dress, who is the father of this theory and who is my PhD advisor, Olaf's PhD advisor, and Klaus's diploma advisor. Thank you, Andreas, and thank you, everybody.